we have the tensor. Okay, so the first thing we're going to do is the really basic thing that people typically do as a first example with deep learning, which is going to be object classification with convolutional neural networks. So we're going to take in some images and we're going to try and predict a class from them. So we're going to be using the CIFAR-10 data set. And this is kind of a data set from, I don't know, about a decade ago or something, collecting, as John said, a whole bunch of blobs that you really can't tell apart of 32 by 32 RGB images. And there's 10 different classes like cat and truck and house and stuff like that. And so we're just going to train a network on this. So again, we can run imports. So practical side of things, like Kevin and also Pierre kind of briefly touched upon this, but if you're dealing with data, then one of the kind of best regularization tricks is to collect more data. But if you can't do that, then data augmentation is the typical sort of thing. So here, we're creating a data loader. It's going to be pulling in this downloaded CIFAR-10 data set. And then we're going to do a couple of data augmentations. So it's going to be a random crop of the image. So we're just going to crop it and then shuffle around something randomly. Maybe flip it horizontally, and also for some extra benefits, someone's calculated the kind of mean and standard deviation of the entire data set, and so we can normalize the data as well, which will make the learning problem easier. Cool, and yeah, so just a note on this sort of data augmentation, right? The point of data augmentation is, that we want to train our model to sort of be invariant to these data transformations. So in this case, we're taking a random crop because, Pierre was walking around and say, if you walk around you don't want the identity of the object to be changing. So in that sense, a random crop makes sense. Horizontal flip, again, the category of an object we generally expect doesn't change if you flip it around. This is natural images, right? If you were to think about classifying the English alphabet, this might actually be a really bad idea, depending on the certain letters. So people have these ideas of data augmentation, but it's also somewhat domain specific. So with images, we might do this. Again, a horizontal flip, depending on your domain, might actually destroy a lot of valuable information. So there's a whole bunch of tricks, you could use hue, saturation, all sorts of things. And question, yes?
Isn't this just a failure of us encoding prime tables?
So I guess one of the things with sort of the philosophy of deep learning somewhat is we take a massive model, maybe it's over-parameterized, and we give it lots of data and we try and expect it to fit to what the true underlying function should be. And definitely, we could impose more priors on our models, and I definitely think this is something that's going to be more and more important moving forward. So Pierre mentioned, for example, convolutions are translation equivariant, but not so much to rotations, but using group theory, people have devised things that are equivariant to rotation and things like that. So certainly, you could say, given my domain knowledge about this, I could maybe actually come up with a model that specifically tackles this sort of invariance or equivariance that I want to be, that I actually want to have, yeah. The simple thing is just to do this, right? you're like, oh, I'm not good enough at like group theory to work out how do I make like a rotation equivariant convolution. I'm just going to rotate it and let the network.
I used to be more like, it seems like it's a one-to-one mapping between what you're doing with data augmentation.
Mm-hmm.
That seems like you could somehow encode it directly because it's all some kind of mapping, right? So maybe you can encode it into model, but I don't know enough about the data.
Yeah, no, you definitely could like encode a bunch of these things into the model. Yeah, so I guess the other thing is like at some point you're like, depending on your data and how general the problem is, you might say, okay, this definitely needs to respect this sort of mathematical property, and in this case you will definitely could think about how can I do this, and then you need far less data, right? But then there might be some things where you're like, this seems like a useful prior, but I don't necessarily want to constrain myself to doing this sort of thing, right? So because everyone picks on deep learning, including myself, let me use an example from another field. So probabilistic graphical models. If people put in like a kind of prior of probability 0, then things can go horribly wrong, because you just assume like, oh, this is never going to happen. Actually, it does tend to happen, but with a prior of 0, like you're never going to recover from it. So again, with deep learning, it's like, well, maybe we will sacrifice a little bit of kind of data sample efficiency and maybe just let the more general version see what can happen with lots of augmentation and regularization and stuff like that. Cool. So this is just a kind of standard neural, yes, question?
About data loader.
Yep.
Can you sample from it, or is it like is it linear that load the full data set in the memory?
So in this case, it would depend on how it's done. But for example, with MNIST, you could probably just like store the entire thing in RAM and then read it immediately out, and that's pretty good. If you're dealing with something at the scale of ImageNet, for example, then typically, like there's several strategies. One way to do it is to store the images and then basically load them on the fly. So in this sort of situation, and this is what PyTorch is quite good at doing, you'll notice like there's a PyTorch data loader, and I've got this argument num walkers equals 4, and that means that it's actually going to load up like 4 workers that are going to run in parallel asynchronously and actually going to be loading the data. So under the hood, what's going to happen is actually like we have 4 workers. They're each going to be like, because I've shuffled the data as well, is they're each going to like load like a batch themselves, a mini batch themselves, keep it in shared memory, and then whenever we kind of call new data, like one of them is going to provide the data, the others are sitting around, like they've already loaded the data, and then once it's passed, like the worker is going to come back and get more data. So this really improves like the efficiency of the throughput, because you're doing this in the background, it's asynchronous to everything else that's going on. Other strategies might be like if you have a lot of storage, maybe you actually store it kind of more natively in like a sort of numeric format or something like that, because then you don't have to like do the image loading, deal with like codecs and compression and all of that. So these strategies can also vary a lot depending on like the size of the data set and like your hardware requirements as well. Cool. So pretty bog standard CNN. We're going to have like convolutional layers, batch norm layers, and we're going to have some fancy LU nonlinearities in the middle. So you can just see this forward pass here. After the convolutions, like we're still going to have activations in a kind of spatial dimension. So just flatten this out into a long vector, pass this through some fully connected layers, and then finally we have the output. So just to go over kind of like the basic training testing loop, like this is super basic. So we're going to create a model. We're going to create an optimizer. So in this case, just like basic SGD, like the dumbest thing you could do, quotation Don Dici. Actually, it's not the dumbest thing you could do. You could do random search. And then we're just going to train it for a little bit. I've got like some helper functions to just plot what's going on. and here's like a training function. So like a technical thing, like we have model.train and model.eval. So some parts of a network might operate differently in sort of what we might call as like training or inference mode. So batch norm is a good example. So batch norm, when you're training on data, like you're going to get an empirical mini batch, and you're going to calculate like the empirical mean and standard deviation and normalize by this. But during testing, what you actually want to do is you want to use like the running average of statistics, so that's been computed over time. And again, same with dropout. So if you're training with dropout, then during training, like you're going to randomly drop out like 50% of the neurons or something. But during testing or inference, you're basically going to keep all of the neurons, and there's a sort of renormalization to make sure the output scale is the same. So this is kind of like just a technical detail, but keep in mind, like we have these sorts of modules in deep learning neural networks, and like I've seen many a time like people use batch normalization and not realize this difference, and like it can make a huge difference to the sort of results you get out, for example, or dropout and things like that. Cool. So again, like PyTorch sort of technical thing, we're going to zero the gradients in the optimizer. We're going to make y hat our prediction from the model based on the data. We're going to create a cross-entropy loss, and then we're going to calculate the gradients from that, and then we're going to perform an optimization step. So this is just the basic training loop, pretty straightforward. And then testing, again, like we can calculate the loss, and we can also do like the actual prediction, like the argmax prediction. This is the thing we're doing. So no, like, the prediction is a kind of 1-0 thing, are you correct or not? But we actually optimize the cross-entropy loss. So there's actually a slight mismatch here going on between like the objective we really want to optimize for, which is like the accuracy, versus the one we actually optimizing for, which is cross-entropy. We're just using this as a proxy. So this is maybe something interesting to bear in mind, because the argmax is, and the prediction is not differentiable, and so we use cross-entropy as a proxy, and there might be other reasons for doing that, because like we have maybe a predicted probability of the class distribution. But depending on like your outcome or what you want out of it, this isn't actually like the technical objective. So some interesting stuff that's been done is if you have like a non-differentiable loss, then maybe what you can do is you can use some of the kind of gradient estimators that Shakir was talking about in the first week. So especially things like the kind of score function or likelihood ratio estimator. Cool. So just going to run it, training testing. Here's one I trained earlier. I've cut out all this stuff, so like basically like the plots will update real time. So I don't think I'm going to be able to train the whole thing during this time. It doesn't take too long, but still. Oops. Need to actually run this. There we go. Downloading the data set. At the same time as everyone else, that was not a good idea. That's fine. I ran it earlier. Cool. So does anyone have any questions on this side of things? No? Oh, yep.
So when you're loading from, or you're not keeping it all on RAM, will that slow down your model a lot to be fetching it from disk on disk then, or where is it keeping it? Is it affecting performance quite a bit?
So it could be, in the sense of like if everything was running CPU in one process, then like yes, the data loading would actually be a bottleneck. In this case, we're using like workers that are going to be running asynchronously. So in this case, like the data loading is not really a bottleneck now. It will actually be like the forward and backward passes of the network will actually be the bottleneck in this case. Oh yeah, that's going to take ages. Let's just kill this. But if anyone else was smart, oh yes, question. Yep. Indeed. Yep. So the PyTorch data loader has this capability. So it's built in for you. So if you use just kind of the default arguments, let's see, like we create the data set, which is Cypher10. We're going to apply some transformations to it. We're going to put it into a data loader, which can load data given us in batch size, and we're also going to shuffle it as well. So every epoch is going to be shuffled. And then this numWorkers for argument is the one that actually activates like this asynchronous data loading. So yeah. So everything else is happening kind of in like the main process or whatever. These are happening in like, can use shared memory or something to like. Yep. Yeah, so you can. Yes, I think they're using shared memory in this case. It's definitely in the source code somewhere. I can't remember off the top of my head. I'm pretty sure it's a shared memory sort of. Yeah, so actually like a lot of these deep learning frameworks, what's happening is it's Python on the front, but at the back end, like it's C++ and all of this stuff, which is why things run quickly. Yep.
Correct me if I'm wrong, because this changes my issue as well. So when you create this data set,
Yep.
you're already loading everything to run, right?
Not necessarily, no.
It depends on which data you're using, I assume.
It would depend on like how they've actually implemented the data set in the back end, yeah. I'm guessing with MNIST, it might just load it all into RAM, or it might not. Yeah, so typically, I guess the other way to do it would be if you've got a huge image data set, is to actually store it as images, and then kind of load it on the fly. So you actually like, the process will have to like read the file, decode the JPEG or PNG and put it into the NumPy array and that sort of thing. But if you're doing it asynchronously, like that's not the bottleneck. The bottleneck will be the forward and backward pass. So that's the typical regime that people might be working with. Yes?
Well, the other thing is that the loading will happen on the CPU and forward and backward pass on the GPU.
Yes, so if you have a GPU, you also have this happening, yeah. Yeah, so if you have a GPU, then it's even better because, it's the GPU will be handling that bit, and then the CPUs are completely free to do this versus like having to deal with like the forward backward pass as well. Cool. So, yep.
Like you were using the functional model for the Microsoft.
Yes.
Because we have two different CPUs.
As in using the NN modules sort of cross entropy? Yep, sure. History lesson. So Torch is actually like a long-going series of like sort of deep learning linear algebra framework. The previous one was Torch 7 in Lua, and the definition and the way it was coded up was that we have modules for everything. Which fits into this kind of deep learning ethos if we have a layer, and then we stack another layer, and we do that about 100 times, and then we're good. So everything was done as modules, and like kind of regressions and means code error loss or cross entropy and loss and everything like that was also done as a module. So something that's been done for PyTorch is the recognition of, well, a module is a nice thing to kind of store a layer with trainable parameters especially. But for a lot of these things, they don't actually have like trainable parameters. They're really just functions, like a ReLU or something.
Thank you.
There you go. So things like a ReLU or the mean squared error loss, all of these things, like they don't actually have parameters. They don't really need to store anything, like initialize an object to anything. So in this case, the simpler thing is just to literally call it the function it really is. So this is the sort of like functional interface of PyTorch versus like this module interface. There's no kind of like best practice per se. So some people will code up networks in a purely functional manner. So they'll do like functional.convolution and then pass in data and the weights as like an input to the function. You can think of it that way. A lot of people seem to go for this sort of hybrid where they'll use the modules to actually store the parameters and then use like the functional interface for things that are generally just functions. Yep.
What is the API for module? What is necessary when you create an object for module?
Right. So, I mean, this is another example of module. So what is kind of going on behind the hood? There's going to be a bunch of like magic going on as well. So the things that need to be defined are basically this forward pass, right? So this says that when I kind of call an instantiation of this, then it's going to be running these functions through. But on the back end, you know, in like the initialization where you'll be putting in the modules and stuff like that, what's going to be happening is it's going to be keeping track of like parameters, whether they're trainable or not, like the hierarchy of the levels, if there's anything like that. All sorts of kind of bookkeeping, such that like you can call the other sorts of functions on top of that, and like it's a nice you know, modular representation of what's going on. So, for example, in the optimizers we call model.parameters. So the model has a function which is keeping track of all the trainable parameters and it's going to return it here. So this is some of the sort of bookkeeping that might be being done behind the scenes. Ooh, skipped it. So one of the kind of, you know, primary reasons people are using deep learning is because they can scale incredibly well to large data sets. They can deal with like very high dimensional data. And so this is just an example of like a bigger, fancier architecture. It's the ResNext architecture. It's going to have like parameterized values and like group convolutions and all sorts of fancy things. It's considerably bigger. You can see like the ResNext blocks. There's several of them, and they're each containing several convolutions and things like this. So this sort of thing, like you would only really want to run on GPU. So I'm not going to be running this one. Again, similar sort of code. In PyTorch, there's a kind of explicit device allocation. So if you're using something like maybe TensorFlow, then it tries to be smart, so you don't have to worry about it. But in PyTorch, the decision was made that we want to know what device things are running on. It's a little more bookkeeping, but it tends to like give you a better idea of actually what's going on. And like, you know, if you want to keep data on CPU until the last minute and then shuttle to CUDA, or like maybe you want to buffer stuff on the GPU, and so it gives you more control over this. And it's a design choice. Yep. Why you might build this as opposed to
what the different components are doing, and then why you might build it in this or that. For someone who's not got a applied mindset, this is like, why do you put these things together?
that's not the deep learning mindset. We just put random things together, and as long as it's like the John Ducci method for like working out things. As long as the shapes match, like we're going to do something with it, right? So to give maybe a little more reason to what's going on, so I mean we've discussed like convolutions beforehand and batch normalization. So parameterized ReLU, it's like, well, you know, maybe the ReLU will create lots of dead neurons, and like a leaky ReLU like gives you this extra slope, but it's nonlinear. But maybe you can get a bit more if we like can parameterize actually like the slope of this thing. And then the other thing is just like it's again like a residual network block. So we discussed why like a residual connection sort of makes sense. And then the final thing that's being done in this architecture is to use group convolutions. So like we have, if you think about how convolutions are done, then we have given a set of input channels, right? 12 input channels and like 32 output channels, then we're going to have 12 by 32 filters. So we're going to have like all possible combinations, right? But what we can do is we can group them and say, well, we're going to get rid of like some of them and just do like 12 to 16 or something like that. So we're going to break into 2 groups. So this reduces the parameterization a little bit while keeping like a lot of expressivity. So people have tried this and it seems to work well, but really it's so empirical, a lot of this stuff. This is not the locality assumption. So group convolution will be channels to channels versus like spatial location. Yeah. Yeah. So it's saying like we don't need the whole like input channels, every input channel mapping to every output channel. Like we can kind of like do a few groups of them and that should be enough. Yeah. So yeah, it's really very empirical. Like people kind of come up with all sorts of things. Like this is driven, for example, by kind of like memory requirements. Like maybe we can do things which are a little bit smaller and get like similar sort of performance. Maybe it even works as a regularization, right? Like maybe the full input to output channels are too overparameterized, and like if we just group them up a little bit, maybe they'll learn stuff. So something interesting that happened with AlexNet, actually for hardware constraints, was that it was distributed on 2 GPUs, and if you actually look at the kind of convolutional filters that were learned in AlexNet, one branch seems to learn like edge filters, and the other one seems to learn more colored stuff. So that was something that happened actually, through necessity, but like you can imagine maybe this grouping has this sort of effect as well. So we'll come up with things. If it works, we'll come up with a reason why it works. That's deep learning. Yes.
So you define these forward pass functions.
Yep.
But they're not actually called in the code. Is that done automatically by the train function, or?
That is done by the fact that the kind of Python calling will be done, and like this is done through the fact it's like a subclass of the module. So if you look in the code, then like it's model, it's the instantiated model. You literally call it as a function with the data, and that's the forward pass.
If we define our own one, we have to call it forward.
Yes, so you have to, the keyword is forward in this case, yeah. Yep.
Just another contribution to that. So because you're subclassing NN module,
Mm-hmm.
the NN module there's already like there's a way you can call a function in Python using underscore call. So it has already been defined for forward function. So anytime you actually instantiate the model, it calls that.
Yep. Cool. So only other kind of fancy thing that's happening here is like a learning rate scheduler for the optimization. So it was kind of mentioned very briefly, but people have been doing things like annealing learning rates, or cyclic learning rates, this sort of thing. And you can see in the training, like here's one that kind of does like a restart. So we're going to train for a little bit. Maybe it settles into like a local optima. Going to bump up the learning rate. It's going to jump out, and then again, like let it go, and then maybe it's going to like come to a lower sort of minima. Again, it's kind of very empirical, and then people try and like come up with reasons why it might work, and then try and study it a lot more. So in a sense, it's great for mathematicians because you can look at all the crazy stuff that people have tried, and then actually try and like see if you can work out what's really going on under the hood. And as Pierre said, like there's so much interesting, phenomena that's happening that we just don't really understand. And maybe batch norm is a mystery that will never be solved. Cool. So that's object classification with CNNs. Any questions before we wrap up? Nope. Cool. All right. So for the next example, we're going to do some sequence modeling. So question answering with RNNs. Again, I'm going to have to download a data set, which I'm not sure I have, so I'm just going to skip this bit. So we're going to be using the Torch text library. Again, we're taking advantage of the fact that we have a very high-level library that's available to us, that's going to like get downloaded data sets, is going to wrap it up in a nice format that we can use in all sorts of helper functions. So for example, like in this case, we have a data set that's already loaded and we don't need to worry about things like the amount of words in the vocabulary, tokenization, all of that stuff. It might help us for that, but like you can see, it's like quite easy to just get started with this sort of thing. So if you were to run this, then this is the sort of, yep, question.
I said a question kind of about PyTorch,
Uh-huh.
TensorFlow in general. I use PyTorch mostly, but I've been kind of informed that sometimes, you can take a performance hit for kind of the dynamic style of PyTorch versus the compiled version.
Yep.
I was curious kind of where that starts to affect things and when that really matters. Like just for industrial like strength machine learning.
Yeah, so I think it really starts to show itself at that level. So, TensorFlow is almost designed to be run at a huge scale within Google, for example. And that's been one of the major design considerations, whereas PyTorch was more a kind of like scripting, being able to get stuff up and running. But, given like highly optimized like linear algebra operations and all sorts of other clever tricks, then actually you can get the sort of like inference and backwards passes like quite similar. So actually, I think like PyTorch may even beat TensorFlow in a whole bunch of like benchmarks of like common models and common tasks and that sort of thing. I think TensorFlow probably has like much better when it comes to distribution. But in the end, you're probably not seeing like too much of a difference in sorts of these things. And again, like the whole bunch of different libraries will have ones where in general, like a lot of them are fairly similar, and then they might have like these odd examples where for some reason one library is like much faster than the other. Like MXNet might be particularly good at something, and Chainer might be good at something, but overall, like you're not going to be seeing like too much difference between them. Cool. So this is the baby data set, so it's supposed to be like simple question answering. And this is going to be one of the tasks, which is kind of answering like a question based on a story, and it's going to be like a sort of one relation sort of task, I think. Yep. Single supporting fact for NLP people here. So what does the model look like? This is it. Hopefully it's not too difficult. So we're going to create like this encoding sort of subclass. So we're going to have an embedding layer. So I'm not sure we've actually really covered this. So if you have a neural network, like you want to feed in like a vector of real valued numbers, but text is a sort of like symbol. So how do we deal with this? So we use what's commonly known as a one-hot encoding. So it's going to be like if you have 1, 2, 3, 4, then your one-hot encoding of 3 is going to be 0, 0, 1, 0. So that sort of thing. And then this is going to be the input of the network, and what we call as an embedding layer is going to take this and then transform it into like a high-dimensional real-valued vector. So if we had a vocabulary of like a few items, just 4 items, then this is going to be the one hot. And an embedding layer is basically going to be a whole list of vectors. It's almost like a lookup table. And so if we had a one hot and we passed it into here, like 0.3 minus 0.4, that sort of thing. And so we have, a token. I'm just going to use characters here, and this is what's going to be fed in. So the network will actually be reading this vector as its input. That's what the embedding layer will be doing in PyTorch. And then we can do, all sorts of kind of matrix multiplication, linear algebra stuff and that. And then we're going to feed it into a bidirectional LSTM. So this is just an RNN that's going to run forward to the end of the sequence, and there's going to be another one running the opposite way. And this basically reduces the kind of length to propagate information, because rather than kind of combining information over time, in one way in the sequence, we're also going to be combining it backwards. And then we can take the hidden states at the different sort of, either at every time step or at the end of the two RNNs being processed, and then use this as a representation of our sequence. So our network is literally going to be one of these encoding things for the story, another one for the question, and the question is relatively small, so it's just going to be a unidirectional kind of standard LSTM, that's all. And then finally, we're going to have just a small MLP on top that's going to be producing the output answer. So these are all the modular components, right? So we have these embedding layers for the story and the question. We're going to take our real valued vectors from this, pass it through RNNs, and then the final thing we're going to do before we kind of feed it into another network to produce the answer is to do some attention. So attention, it's a fancy word. In biology, it's lots of amazing and crazy things. In deep learning, it's just a fancy word for kind of multiplication. So you'll see that this attention is basically being done through Einstein summation notation in this case. But the basic idea is attention in all its biological glory. It's literally just going to be sort of like outer product or dot product or something like this. That's all it is. But nevertheless, it's in a sense a powerful mathematical operation in terms of you have a multiplicative interaction between two sorts of elements. So it makes kind of like the interaction between these elements a lot more than you would have with just an addition. So training and testing loop, you can see that it's actually pretty much the same as we did before, right? Like there's nothing much difference in there. We create the network, the optimizer, plot, train, test, and we're still using the same cross entropy loss. Like we're just trying to predict, tokens here. Question? Yep.
Sorry, can you go over the Einstein sum like the sum?
Oh.
Just to explain.
If my display comes back, what's happened here? I have been signed out. Does anyone know? I mean, I'm still running it here. I don't know what's really happened with the display. I'll try plugging it out and in again. Deep learning approach. Did that work? Oh, maybe. Nobody has any idea. Okay. All right, I'm going to have to do the rest of the tutorial through interpretive dance. Einstein summation. Okay. BSH. Okay, thank you. Okay, perfect. Okay, thank you. Tobias. Okay, perfect. So, nice thing about Einstein summation is, typically we'll be doing our linear algebra, we'll be doing operations. For those of you who haven't seen it, this can be quite nice because it makes it quite clear what axes we're sort of operating on. And thankfully I had the foresight to kind of use good like letters of the alphabet. So this would be batch, this would be story, and this would be like the hidden size. So what's going to be happening is we have sort of batch dimension. We're going to have like the story length dimension, and we're also going to have like a hidden dimension. And for the question, what's going to happen is like we're going to have a batch dimension and a hidden dimension. So we're basically going to be subbing out over this sort of dimension. So you can see like the batch is retained and the story dimension is retained, but the fact we've lost the h means that we're basically summing over this. So we're going to have batch by sort of S size coming out. Any other questions in the meantime? You really want to see me dance, huh? Question, thank you.
So I'm wondering about not a technical question necessarily, but more of a design question.
Mm-hmm.
In most of these examples, and many examples of other pipelines that I see, people will generally just kind of specify the entire network in the module setup, right? Like in the convolutional network example, we'll see like con1 block, con2 block. If you're trying to iterate with lots of different architectures and you have kind of multiple different modules you might be using in different places, do you have any suggestions on how to best organize the code, or just certain tools or design paradigms to make the management of these things easier, so that you can reuse code more effectively and more effectively have these kind of modular structures?
Yes, so the fact that it's fits into the imperative coding style, like you treat this a lot just like normal code, means that you could kind of parameterize generators of networks fairly easily. So for example, like a common thing to do is, we'll have a few initial layers of a convolutional neural network, and then we're going to have, X amount of residual layers. So literally what you would do is have as an input to the initialization of the network, number of hidden layers equals, 100, and then there's going to be an iterator that literally like stacks on layers. And then in the forward pass, it's going to be literally, it's going to be running for this many layers. So in terms of having like different sorts of depths, like that's one way to do it. Again, width is something that's just a straightforward parameter. And modules, again, like you could create like a residual block, like the other sort of residual block, or a res next block, make these kind of different modules, and then within like the kind of bigger wrapper of your neural network, then you just take a string argument that says if it's this, then we're going to be using this sort of block, and just use if statements and all sorts of just programming things as necessary, and it works out fairly neatly actually. Cool. Yep. I believe it's just a one-layer LSTM, yeah. I mean, it's going to be running over the entire sequence, right? It's just looking at one input token at a time, yep. So yeah, if you, there's various strategies for this, right? So if you have a stack of LSTMs, right, again, it's going to be similar to stacking convolutions, like the higher up LSTM or RNN will be able to take in some of the context that the other LSTM has. Neural networks are modular, so you could be combining these with like convolutions at the beginning, dilated convolutions, all sorts of things, which would kind of like have a larger receptive field before you feed it into an RNN. You could be having like a mix between like convolutions and RNNs, and like there's like things called quasi-RNNs, which are actually some sort of hybrid between them. So really, when it comes to deep learning, like you can think about, oh, what are the sort of properties of the data that I really want to be able to capture? So convolutions, which are particularly successful for natural images, and it's because we have like this idea that natural images have a lot of like shared local statistical structure, so things are like really shared over time. You can apply this sort of thing to, for example, spectrograms of audio. So if you have audio, like you can do a sort of Fourier transformation. In that case, actually, like the two dimensions that you're operating on are not the same as they would be in images. So maybe you do kind of convolutions in one direction and convolutions in another direction. If you're dealing with text, then you can have like something processing like one token at a time. But there are alternatives to this. So the transform module was kind of mentioned beforehand. So just to go over some kind of two other sequence models, so RNNs kind of make sense, like they run over a sequence and they're doing this update internally. But some other sequence models that have been applied successfully to text include even convolutional neural networks. So if you think about the history of NLP, then like a sort of representation of text that was very common and actually can be quite strong for a lot of tasks is called a bag of words, where you literally just kind of have features for all of your different words and you don't care about the order and you just group them together and say like, this is my representation. So if you have like the cat sat on the mat, then you kind of have the features for all of these. You can have, you know, double for the because it's in there twice. And this sort of representation can be passed into another sort of machine learning algorithm. So when it comes to sequences, like people have used convolutional neural networks because we think about locality in text, like words are coming in a sequence and we can kind of operate convolutions over them. I'll have to erase, but so we could literally be running a convolutional filter. So this is it sort of running over. And then it's going to be giving us an output, right? That's kind of similar to the sequence length, depending on the padding. And this is, again, another way that you might think about representing the text. So it's much more directly taking the local context into account with operations that are kind of simpler than the actual kind of recurrent processing that's going in an RNN. So convolutional text models have had a reasonable bit of success. But thinking a little further about this, we mentioned earlier that convolutions are kind of translation equivariant. So a thing that's commonly done with a model of this sort where we also want to keep the sequence information, and an RNN would be keeping this in its internal state, is to actually kind of provide this externally, which means that people use what is known as positional embeddings. You can call it feature engineering if you want. They'll literally feed in like kind of these functions based on sign and costs that kind of the network can use to work out what position it is within a sequence. So convolution wouldn't be able to work out if it's like at the end or at the start of a sequence, but if you feed this information as an extra feature, then it can also keep this. So you have like the nice local structure and then also this sort of external input that gives it this extra information. And so the other model, which is kind of very popular at the moment, is this kind of attention or transformer module. And again, that's basically taking in all of the sequence at once and basically performing attention against all of these things together. So exactly the same sort of attention that's going on there, just a little bit more complicated. And And in that case, like people also use these sort of positional embeddings so that like the network can work out where it is within a sequence, because we'll consider relative position to be important. And the reason that it's been so successful, there might be many reasons, we don't really know everything, is we've discussed earlier a lot about the difficulties of gradient propagation and how, hence like credit assignment in recurrent neural networks. Well, if you can kind of see all the context at once and do it through like some, linear operations and things like that, then the credit assignment and backpropagation problem is much easier. Like we don't have to deal with the fact we're reading one token at a time and applying like a nonlinear operation that could, destroy data and have to backpropagate through a lot. Well, it's like the start of your sequence is connected to the end of your sequence as anywhere in the middle. So these are these transformer attention modules. Cool. So just to wrap up with this notebook, here is just testing the trained network on it, and here is actually the sort of attention mask that we get out of it. So at the top, we have the question, where is Sandra? Here's a little story, and you can see that after a bit of training, the kind of attention mechanism, which is just this multiplication, has really put a lot of attention on the final occurrence of where Sandra is. You'll notice, like, even though Sandra has appeared several times beforehand, this network in this case has seemed to learn like where it actually needs to focus. Question?
Sorry if you went over it, but what is the output of the generator? Because it seems it's a long vector of 0 and 1, or it's not using the same embedding as the right? It's just
The output of this network?
the generator, the final one.
So the output head is basically going to be classification. We're going to predict a certain word.
But it's not in the same embedding space as the right?
So in this case, it's actually, so it's not in the same embedding space. In fact, it's not even outputting an embedding. It's literally trying to output like the class itself.
Isn't it easier if you output an embedding rather than trying to output a single word?
So I believe there have been some papers which have been trying to look at this, but then the difficulty you have with this is if you have a large vocabulary and then you're trying to predict like a 32 or 512 dimensional vector for everything in the vocabulary versus like just the one number that you need to put through a softmax and predict a class. So I believe there's been some work looking at this and saying, oh, well, actually, if you try and predict the embedding as a target, like that can work quite well. But so there's lots of NLP problems when it comes to vocabulary size and things like that. This is operating like a normal kind of class, like over multiple classes. But for NLP, people have devised things like sampling approaches based on like noise contrastive estimation or hierarchical softmaxes and all sorts of tricks to try and like reduce the problem of having a very large vocabulary size. So again, this is a sort of simple solution to the problem, like it's the most basic one. But definitely like there's some issues and maybe we're not getting the best out of these things, and this is an area that's ripe for research in terms of like maybe this could be improved somewhat, right? Cool. So you are all NLP experts now? Not. Okay. But hopefully the thing with this is that, you've seen how an RNN works. It works over sequence. Maybe you can do attention over multiple sequences. And this is just a module, so you can stack something else on top. You can have like a convolutional neural network and, do some like captioning based on the images, and you're just sticking all of these networks together and you're training them through backprop. Yep, question?
Do we have a correlation between LSTM or GRU?
Hmm.
I see more examples with LSTM, but GRU is a bit more simpler than LSTM. Has there been any proof that is actually says that this is much better than that or the other way around?
Where are the IDSIA people? Are they not here? IDSIA. Come on, Jürgen Schmidhuber's lab. Have they all decided to Skype because they... I see them over there. Okay, you can explain yourselves. Oh, they're hiding. Okay, they're hiding. So they will correct me if I'm wrong, because that's what they've been trained to do. Yeah, so the LSTM was devised. It has this kind of internal feature, this constant error carousel, which can theoretically like propagate information for as long as possible. One of the things behind the GRU is this sort of idea you can couple the sort of like forgetting gate and things like that. And this simplification seems to work quite well for a lot of problems. And like it has also slightly less parameters because of this. So for a lot of people, like it tends to work out pretty well. Theoretically, I believe the GRU only has a sort of finite context in terms of like how much information it can remember, because of the fact these things are coupled. Whereas an LSTM can learn how to count is, yeah, okay, they're nodding. Yeah, okay, that's the one. So theoretically, there is some stuff that an LSTM can do that a GRU would not be able to do. In practice, for a lot of problems, this may not be an issue.
Also,
Yes.
is there a challenge to like train, like even though LSTMs have an optimal, like they have this higher bound on the GRU, like isn't it hard to train LSTMs to get to that potential usually, which is why, I mean, it seems like these recurrent networks are a bit hard to train in general.
So yeah, recurrent networks are hard to train in general. When it comes to the kind of abilities of RNNs, there was a nice paper, I think maybe a year ago, something that showed like with a lot of effort, you can get like vanilla RNNs to do a lot of the same things LSTMs and GRUs do, but just getting things to train, it's much easier to get a gated recurrent neural network to work. So this thing which kind of explicitly goes getting between the input and this sort of hidden state. But in terms of difficulty of training, I don't think LSTM or GRU are like particularly much different to get training. Am I supposed to say LSTMs are better, easier to get training? Yeah, they're okay. Okay, fine. I'm allowed to say this. Sorry, Jürgen, if you're watching. Question?
I mean, how much bearing does this theoretical properties have in practice, though? I mean, like, you have, like, what, feed-forward networks are, like, universal approximators, but you don't throw that in a paper and say, let's go home, you know, we're done.
Yeah, so in terms of, like, these theoretical things, there's, I guess there's two aspects. One is, like, the fact of gated recurrent neural networks and the way they actually try and account for the fact you have like these vanishing gradients and loss of information. That has worked. Like that really does work. Yeah. Whether this sort of capability of like being able to count or not is actually important, it would really depend on your task, right? So it seems for a lot of tasks that people actually use that a GRU would probably be sufficient. But you know, theoretically, there are some tasks, and it really depends on your definition of like how important is this task? Do I really believe it needs these capabilities? And in that case, you'd say, okay, well, in that case, like I really would need to use an LSTM.
But for example, how brittle are these properties? Would using floating point numbers make these properties disappear?
So floating point numbers will, you know, technically like destroy a lot of these things. But I guess in like practice, when you know, people actually do these experiments and show like this thing just cannot learn this and this thing can learn it. Well, they're doing it with floating point numbers. So like in practice, you can do these things. So when it comes to like, there's tons of work going into like RNN architectures and things like that with all sorts of fancy properties. It turns out a lot of people have tried very hard to beat an LSTM and they're really, really hard to beat. So all of these fancy things might have some nice properties and people show they do better than LSTMs, but some of these tasks might be quite contrived. And so for tasks that a lot of people work with, you know, like a GRU and a standard LSTM seems to work well. But really, if you really do consider these problems to be, you know, very interesting or very important, then maybe you do need to pay attention to like what the sort of capabilities of these different things are. So I think unitary RNNs was something that's mentioned, like because of the structure of the weight matrix is, kind of keeps the variance of the activations within a certain range, helps with propagation of gradients, all of that. And certainly, so like people will come up with, this is the sort of mathematical construct, it has these properties, and we do observe them in practice, but then the question is, for the task you're actually looking at, are these properties really necessary? So, a good question is if people have seen the text that's generated from OpenAI's GPT-2, like it's just learning on a massive data, and it's really just learning statistical correlations, but it can learn this crazily rich, almost human-like language. And it's really a question of, like, does language modeling really require a lot of structure or prior knowledge about the world? Or, if we had a big enough data set and a big enough transformer, could we get, there? And it seems like we keep on pushing the boundaries, and we can get close. I doubt we'd be able to get, truly human-level language understanding, but it's impressive how close we can get to certain things with kind of dumb neural networks that are big and trained in lots of data. Cool. So let's move on to breaking neural networks at the end. So to kind of wrap up like some basic stuff with neural networks, we're going to discuss, well, what happens if you take a trained network and rather than optimize the parameters of the trained network, we optimize the input with respect to some other objective. And out of this, actually quite a lot of nice stuff happens. So in this notebook, basically we load some images. We've got a panda, or maybe a gibbon, if anyone's been working on adversarial examples, and Van Gogh's Starry Night. We're going to take a pre-trained VGG network, so this was discussed. This code also has like a sort of normalization layer, which I've made because it's been trained on like normalized ImageNet data, so we just need to make sure that the network gets normalized data as input. And we're going to make a saliency map. So you'll notice that we're going to call the model on some data, and then instead of explicitly formulating an objective, what I've done is said we're going to propagate a certain vector of gradients through the output, and that's just zeros everywhere except one on the sort of correct class, and this sort of corresponds to, well, I really think this is like the panda in this image, and I want you to kind of do your backpropagation, like how would you improve this classification? And if you backpropagate all the way to the input, then we can see what is the network kind of looking at, like where is it putting its attention? And we can see like noise. So technically, like we have an objective that's going on when we're backpropping through the network. So this is the end of the optimization problem, but it's not very interpretable. So with a slight change on the gradients that's going on, this is a technique called guided backpropagation. I'm not going to go into the details. It's just there. It's basically zeroing out some of the gradients in the ReLU. We'll notice that the network is now focusing kind of directly on positive aspects of the classification rather than the negative ones. And we'll see this sort of panda face appearing. So in this case, it's almost the same sort of objective. We're just modifying the gradients a little bit, and we can get something like this. And this is very nice. So we say we've trained our black box model, and we can get some sort of interpretability of what's going on, which is somewhat true. Question?
What does the scale on the right mean? It's dark gradient, like it's what? Low?
Yeah, so it's... Am I doing anything with it?
It's moving from white to black.
Right, okay.
Yeah. In this case, basically just look at like the magnitude rather than like the offset of the magnitude, right? I don't think it's particularly informative in the case of something as qualitative as saliency maps to like really think about, you know, whether positive or negative has so much of an impact. So we're going to take the same sort of procedure and do feature visualization. So what I'm doing here is I'm basically taking VGG, I'm taking several copies, just cropping off the network at several layers. There might be neater ways of doing this, but this is just a quick and easy way. I'm going to feed in some random noise. I'm going to pass the inputs into an optimizer, because, you know, I can use the optimizer to solve this problem. And I'm also going to like apply some sort of tricks on normalizing the gradients and whatever. But in the end, you'll see like we're passing in this noise into the network, and we're going to try and maximally activate certain filters, right? So we're taking the output of some intermediate layer, and we're saying, okay, well, you know, our loss is like the negative of the value at a certain filter across the entire thing. We backpropagate this, and we can go through to the input. And here's some I trained earlier. Let's zoom in. So let's look at the network. So 6 layers, 13 layers, 23 layers, but this is including like ReLUs and things like that. So it doesn't correspond to like number of convolutions. And you'll see that kind of at the lower level, we just have things that are a bit like lines, maybe a bit wavy, a bit of texture, then something a bit more textured, a bit of color in it, and then towards the end, and this is not a particularly deep network, so you might not see anything like very like high level, but you can kind of see like these sorts of like textures or even motifs maybe appearing. And for some sort of like practical reasons, I'm applying some sort of like regularization on the data and the gradients to get better visualizations. There's some fantastic work done mainly by Google Brain people, and it's available on distill.pub that really looks at the kind of like visualization of neural networks, and they have some really beautiful stuff going on, so I highly recommend checking that out. And it's also great for kind of understanding like what might be going on with neural networks. If you've heard of Deep Dream, same thing applies to Deep Dream. It's just applying this sort of feature of visualization to an existing image. We're basically accentuating parts of the image that the network is looking at. So you can see like maybe some eyes appearing in random places. Maybe that's a dog snout because ImageNet is like 20% dogs or something. So yeah, if you see like these kind of like puppy slug things in deep dreaming sort of images, it's because ImageNet has like a ton of class imbalance in terms of dog breeds. So it is actually a reflection of the data that we see these things. Same technique, we're going to do style transfer. So that's why we had Starry Night, very famous sort of application for like creativity and all sorts of things. Again, use the same sort of models. The sort of trick that's going to be going on here is we have an objective that's going to be based on actually two images. We think of like a style image and a content image. So we want to create an objective which kind of recreates the content of a given image, but also has the style of another image. And the question is, how do you quantify this? How do you make this into an objective? So in this line here, you can see content loss. So we're going to be taking like the output of the model fed like the kind of content image. And we want to make sure that, so we can start from like a random image, and we want to make sure that intermediate features at one level of the network of convolutional layer is going to match the same sort of features we would get out when we pass in the content image. And so we're minimizing just an MSE loss in this space. And this sort of, we think, corresponds to maybe a rough idea of content, where things are. The star loss, however, is based on the gram matrix of activations of the style image. So this is basically looking at textures. So rather than looking at like the kind of coordinates of where things are, it's actually kind of using the gram matrix and considering this sort of like textual space, and we want to maximize this. And so if you maximize this, if you kind of optimize for this loss, this is the sort of thing that you might be able to get out. Not sure I've downloaded everything, but if you run this yourself, then you'll see like it kind of starts out as a starry night background of like blue and yellow splodges, and then gradually like the panda will start to appear. So again, it's the same sort of idea. We're just applying a slightly different objective. Now we've got 2 images, and we can get this sort of thing out. Adversarial examples. So we're not done bashing deep learning enough. So let's talk about adversarial examples. So we've been going through this idea of let's put in some input to a network, a trained network. Let's optimize some objective with respect to the input. And we can, by changing the objective, we can really do lots of different interesting things. So everyone's favorite, it's the banana. I made this change last night. I hope you appreciate it. This is 96.65% a banana. If you don't believe me, you can run it yourself and trick the network into this. So what are we doing here? Like, we're just taking random noise. We're going to set the sort of gradients for the objective to be the banana class. We want to maximize the probability that the network thinks this is a banana. We're going to optimize for it, so just gradient descent on random noise, and bananas. So a network that we think is intelligent, like classifying pretty well, lots of different natural objects, thinks this thing is a banana or a bunch of bananas, and if that doesn't worry you, you should be a little bit worried. And we can also do sort of direct, yes, question?
Have you seen any examples of someone doing this and actually getting a nice image of a banana or something like that out?
I'll get to this in a bit. I have something interesting to say about this. So we can also do a sort of like more directed attack. So this is a panda input image. Here is the panda or gibbon or banana after an adversarial attack. And here is the noise that's been applied to the original image, just kind of scaled up so we can see it. I realized like there might be projector quality issues, but even on my fancy Retina screen that I paid way too much money for, I really cannot tell the difference between these two. So this network is just really being attacked by this high frequency noise. And it thinks, with close to 100% probability that this thing is a banana. Yes.
So how do they generate this?
It's this code. So let's step through. Okay, so we fit in the original image, right? That's going to be the panda. We are going to look at the probability outputs of this. We're going to find like the banana class, and we're going to say, actually think that this thing is a banana, right? But then rather than adjusting the network's parameters to make it think it's a banana, we're going to adjust the input through gradient descent to make it think it's a banana. So yeah, we're just like literally adding a little bit of the gradients with respect to this objective, and then projecting back to 0, 1 for the image. And that's it. Yep. And yeah, so that's it. Like close to the state of the, well, it's a really, it's just so few lines of code, and you can get these sort of results out. Yep.
If you don't have access to the model,
Mm-hmm.
it's still possible to get those adversarial examples, right? If you don't have access to the grid.
Yeah, so in terms of security, people think about like white box attack, black box attack. So this is white box because we have direct access and we can like do all these things. Black box attacks are possible. It really depends on maybe how much information you have. One thing that people seem to have found is like adversarial examples are transferable. So if you have a rough idea of what model it was, you can create them there and might be able to transfer them. But you can use, even if you have like, say just the top class probability, it's very expensive, but you could use an optimization technique to try and find things that fool it. You just have to attack a lot. So it is possible, and like it really depends on like how much access to information you have and things like that. So to go back to the earlier question, what can you actually get a genuine banana out? Well, actually the sort of like feature visualization tries to do that. So what people have been doing for a long time is they've been saying, well, if I apply this sort of like feature visualization objective, then without regularization, I'll get something like this. If I regularize it, I get something like this. There's been work like kind of inverting like an image generator like a GAN. That was like some of the first examples of really amazing feature visualizations. And people are basically saying like this optimization problem is ill-posed, right? Like we want to project back into the domain of real images. We don't want to project into an arbitrary like real valued space. So we should like be constraining using priors or like any sort of regularization. So early work is like using total variation norm and things like that, and really trying to constrain it, back this optimization problem into something that looks like natural images, and then we can produce like really amazing images and visualizations. But adversarial examples actually kind of turns this a little bit on its head. It's like, well, these networks also seem to be doing stuff based on like high frequency noise. And basically a lot of recent work has been looking at, well, for a lot of tasks, object classification, things like this, neural networks seem to be able to learn from noise. Recent work that said actually like this noise distribution might even cross between like the training and test distribution. So this is actually for a data set even a valid feature, like looking at high frequency noise, to be able to generalize properly. And the network's just optimizing this objective, and this sort of thing works, and it fitting into our idea of generalization. Which means that actually when we do these like feature visualizations, when you're trying to invert a network, and we see noise, actually like the network is kind of looking at that too. It could be, right? And we're just imposing so many priors so we can get pretty pictures out. But actually, like if we didn't, we actually could be looking at what the network is looking at. And so there's quite recent work that said if you do feature visualization on networks that are trained to be robust to adversarial examples, so adversarial training, then actually the feature visualizations you get out are already like a lot more kind of natural looking. So this is kind of like recent work that's been going on. So yeah, like this maybe brings into question like maybe we need more priors in our networks. If we think that, say, for humans we know that shape bias is important in the visual system, then maybe we should be finding ways to inject this, but then there's also, depending on the task you give the network to do, it might actually be learning things that are closer to shape. Even in these sorts of object classification tasks, you'll see a network might pick on a zebra stripes because it thinks that's very easy to classify, and like this is all textual information, and it turns out for this task it's good. But there's a paper I saw where actually like for certain things, like maybe a trombone, doesn't really have much in the way of texture, but it has a very distinctive shape, and then the network will learn this. So yeah, it's a function of the network, the training, the objective, all of these sorts of things, that things are going on. So mystical creatures, these neural networks, and we're really starting to like uncover some interesting questions, not just about like what are these neural networks doing, but I think hopefully they question like the objectives we train for, the sorts of things we're doing. There's no free lunch, right? Very sad, no free bananas. Cool. Question?
I wonder if you could offer your perspective on, so given what you just said in terms of adversarial examples and how these high-frequency features actually may generalize and kind of be valid features in the sense that they're present in our training or test distribution, they're present in lots of natural images. So I wonder if you could offer commentary on if that's true, why is it a problem that these adversarial examples exist? Why do we care as much, or why is it so unsatisfying to us to see these networks having this kind of bias?
Yep. So I agree. Like this is the sort of presentation of this work is like they're doing the right thing. Like we tell them to do this, they're actually doing this, and like by all sorts of metrics, like even generalization, like they're doing the right thing. But to us, we see these things and we're like, they're kind of dumb, right? And it's because we have so much biases and priors about the world around us that we use to make decisions, and we kind of expect like artificially intelligent systems to try and come up with the same sort of priors as us to solve tasks. I think it's an open question whether, we have so many priors about the world that could be suboptimal, and theoretically there could be agents out there that don't have these priors and are able to actually do better in terms of some sort of objective. But if you think about humans or human-level intelligence as a sort of goal, then we have this sort of bias. We think quite highly of ourselves. But the sort of priors that we have about the world are generally the sorts of ones that are correct and that we would, hope to see in intelligent agents. And also maybe from a safety perspective, people would certainly think that systems that think and have similar priors to us would be kind of easier to communicate with and might have better aligned values, something like that perhaps as well. But yeah, I mean, humans are certainly suboptimal in lots of senses, but then it's also a question of with respect to what sort of objective, right?
There's some work like that shows that CNNs appear to be kind of texture, like so it also reveals some of the biases of the original architectures, like very texture biased, and you can like ameliorate those things with like, sometimes it has more to do with the data than the actual architecture. So if you start messing with the actual data, you get much more. So like I guess also if it's doing poorly on a very constrained data set, like you mess with things, then you can't really expect it doing a wider range of data sets maybe to do as well if you don't understand why it's. So.
Cool. So I think we have about half an hour left, so I'll go through fourth notebook. So for the fifth notebook, which you can kind of look at in your own time, it's looking at some DeepRL algorithms, but also considering that Katja is going to be talking about reinforcement learning this evening and tomorrow. I won't have to introduce RL now. You can kind of look at it as extra after her course in reinforcement learning if you want. But let's just quickly try and get through some of the deep generative models.
Can I say something?
Yes?
So I will update the Docker so that you can run it from the Docker with the reinforcement learning stuff later tonight, but I'm not getting it done like right now.
Okay, cool.
So it'll
Thank
be
you.
sorted out, but-
Thank you. Cool. All right, so we're going to learn to produce MNIST digits, not celeb A beautiful high-resolution faces. So this sort of stuff you can hopefully run on a laptop in like 10 minutes or so, maybe some of these examples. So again, let's do some imports, let's do some data loading. Let's look at a variational autoencoder. So again, we have some convolutions, some batch norm layers. In the middle, we're going to have like a vector of our latent space. It's going to be a parameterized normal distribution. So you can see like I have fully connected layer for mu, the mean, and one for the log variance, the standard deviation, or we can get it out from that. And then the decoder is just going to be these transpose convolutions. So For encoding, we're just going to pass through an image, flash. So if we look at the training objective, again, like there's just a little bit of boilerplate, but the objectives here is going to be reconstruction loss. So our observation model, what we are trying to produce, log probability of the data. We're going to assume it's kind of like bounded between 0 and 1. Think about it, log likelihood of a Bernoulli distribution, and so use like the binary cross entropy loss. And then we have the KL divergence here, which I've written kind of out in its kind of basic form, given that we're just working against a normal 0-1 distribution as our prior. If you were to think about implementation, you could also try and directly output like an object that is a normal distribution and use higher level functions like normal distribution .kl divergence against a thing. So in Chakir's notebook, this is one of the easier solutions, is literally to use like the KL divergence function in the library directly rather than coding it yourself. Certainly if we're thinking about conditional VAEs, so we'll have like a learnt posterior and a learnt prior. We want the KL divergence between these. This would be easier, for example, to use. And so we just sum up these losses and then train it. And here are some samples from a trained model, and then on the right is a kind of just a linear interpolation in the latent space. Any questions on this? I guess it should be easy enough because it's from the Chakir's tutorial. Yep.
From the linear interpolation, like, can you kind of going from 0 to 3, it looks like? Is that just like tweaking one of the latent spaces that seems to represent 2 digits? Like in the image.
Oh, yeah. So this is like, you know, you train it, and we don't really have any idea what the latent space would correspond to, but in these 2 dimensions, it seems to be like learning something like this. Yeah. Cool. So one of actually the questions in Chakir's tutorial is like, why do the samples not quite look as good as the reconstructions? So when we're sampling from a VE, typically what we do is we sample from the prior, but remember, like the learned posterior of the model doesn't necessarily correspond directly to the prior. Like it's going to be constrained to be close to it, but it's not exactly that. Yes, question.
I got a question. So you just said like there's a linear, you do a linear interpolation between these 2
Yep.
embeddings in feature space, and then you get these kind of like images.
Mm-hmm.
Why does that make sense? I mean, why do you get something that is kind of meaningful? Is there like some sort of like geometry in the latent space that, or feature space that generates somewhat reasonable pictures that look like linear interpolations between 2 images, 2 digits? Why don't they live like on a circle instead of like a straight line?
They live better on a circle. So for this simplicity, like it's, I'm using linear interpolation. But yeah, it's true. Like they would be living closer to this circle. Yeah.
I'll actually answer that.
Oh, thank you.
Yes, you're absolutely right. Like ideally you want to do geodesic interpolation, and this has been done, for instance, in the paper by Tom White, which was called spherical linear interpolation. We don't really have a theory as to why that works. So like people have not really like manifold theories, but overall it just works better empirically if you assume like constant curvature because you're projecting a Gaussian system. Oh, but that's going to work much better.
Yeah. So this was purely like the simplest thing. I agree. Like spherical interpolation makes more sense. Yep. So why is there structure in the latent space? Yeah. So I think there's many possible ways to explain this. I'm just going to go for maybe a bit of an information theoretic perspective, which is like you can look at this as a sort of noisy channel. So what's happening is like we have like this prior, and we're going to be passing samples through. And because of the noise, it's not like they're corresponding directly to these points. There'll actually be, this distribution here. So if you want to be able to kind of code your data and reconstruct it well, right, you are going to have to like make sure that points are ideally kind of like reasonably separated in the space. In practice, this is not going to happen perfectly.
It would be any weird shape, right?
Well, I mean, so like each of the points is going to be represented from a sample from distribution. So like we have this amortized variational inference, like we have this normal distribution per point. So in the end, we have like this sort of like distribution around the encoding of the points. And a restricted capacity in the sense of like we maybe try and constrain it to this sort of normal distribution. So if you do that, then probably a good way to structure how you like construct your encoding of the data will be to do it in such a way that like nearby points like correspond to sort of like very meaningful qualities of the data. In general, this would happen anyway with autoencoders, but an autoencoder can have like the entire domain of the real. So what the autoencoder will be doing is having a point here, point all the way here, and like it's perfectly good to reconstruct the data. But under these sort of constraints, then it would even more force maybe the encodings to like lie along like slightly more meaningful manifolds. And this is just one perspective, right, on like an explanation for why these things might be learning like some nice meaningful manifolds. But yeah, in general, it seems like for a lot of deep learning models, we see like these manifolds appearing. So for people who've seen like the emergence of word embeddings and analogies, it's like king is to queen as man is to woman, and these are literally just kind of like Euclidean arithmetic operations of plus and minuses. So it does seem like a lot of these neural networks do learn like these kind of manifolds, so locally Euclidean things, where we get these properties out. And you might expect that it is a reasonable strategy to be able to cope with the task, right?
So if we tighten the KL constraint even further, like in beta V, will come back.
Right, so exactly why this idea of like tightening the constraint in the beta V, they think corresponds to like really spreading out the, like really controlling like the factors of variation and making them somewhat independent. Yeah, but like this whole field of disentanglement and beta VEs, it's a great sort of motivation. I think the original work is people are kind of slightly calling into question like exactly what's going on. And so yeah, there's a ton of interesting work going on in this area in terms of like, is this the right objective? Like, what are the interpretations of like beta VE? And like, how can we define disentanglement? So nice work on like, maybe we think about equivariances in group theory, things like that. So yeah, lots of interesting work in this area. And I think like a lot of things, a lot of interesting interpretations. Just like with GANs, we can think of dynamical systems, we can think of game theory. There's lots of interesting ways to look at the problem and try and understand what's going on with these things. Question?
Just a small technical question. So here, we assume that we get a log variance from the encoder. And in the morning, like Pierre told us, that another option would be to use a self-class activation variance. Is there any reason to prefer one over the other?
So I think the soft plus tends to be slightly better behaved in terms of gradients and whatnot. So that might be a reason to like do that, get a variance out, but there's no real deeper meaning behind it. you could go log var and just x. Cool. So it might look like we're going from crummy digits to crummy digits, but I promise you the right hand is a little bit better. So this is just a kind of nod to the notebook that Shirk here put together, and it's, well, if we sample from the prior and our learn posterior doesn't quite match this, then is there some way of like improving how we're sampling? And one way is to actually perform like Markov chain Monte Carlo sampling using the chain network. It's really simple. You just sample from your prior, push it back through the VAE again and again, and this sort of approximates MCMC sampling. And we'll move basically the samples from the left to the samples on the right, and you'll see that they generally correspond to like things that seem to be kind of higher likelihood in the data. So we're running loan time, but here is code for importance-weighted autoencoder. So reconstruction loss is the same, but you'll notice that like these 3 lines here are corresponding to this sort of like multi-sample loss. So unfortunately, like previously with the VE, we could use like this analytical KL divergence. The multi-sample loss doesn't have quite this, like sort of includes multiple samples and is slightly more complicated, but this is the loss here. And just to note, like, kind of one of the motivations for the importance-weighted autoencoder is we're getting like a closer bound to our true objective, but it turns out for various reasons that this may produce worse samples, and it's to do with reasons of like the decoder maybe not learning as well, given like a better inference network and various things like this. So again, just to highlight, like we typically optimize, come up with different objectives to train for, but sometimes we train them and then we find the things work out differently than we might expect for various reasons, and it's this kind of trial and error exploration in deep learning that really can like drive further research. Like we try something random, we particularly think about when it comes to RL and control. It's like, well, prediction or reconstruction might be like a really not that great an objective if you want to control something in the environment. Oftentimes, like in an environment, you might be controlling something very small. If we're talking about like trying to really predict an observation, well, we can predict the background very well, but we can't predict like a small point, and that's the thing that's important. So certainly there's an idea of like downstream tasks might really have to be incorporated. But it could be that the right sort of objectives and priors could get you like a decent sort of representation, and just the reconstruction loss that people are using is just a bad one. So there's definitely, I think, an interplay between you can have maybe some general purpose kind of tasks, unsupervised, self-supervised, semi-supervised, and then feed them downstream. And maybe it's a question of working in the right data and the right tasks, but probably also like things from downstream need to be considered. Yep.
Two points to follow up with what you said. One is that I've seen work on shaping the latent representation just for interpretability, not necessarily for another task. So a class like Jonas digit or something. The other one is like, I think a reasonable, like, a intuitive argument against reconstruction as a good loss predictor for a test is that like,
So I guess maybe the argument is like maybe we can reconstruct well in some high-dimensional latent space. So definitely, there's been a lot of work on like, oh, we don't do our reconstruction loss in pixel space, we do it in like VGG feature space or like some downstream encoder, and that corresponds actually much more to the sort of objectives that we're trying to do. So highlight some work from DeepWind where they're looking at beta VEs and disentangling latent factors, and then actually try and do reconstruction losses in this and show like they can learn interesting like factorized features that can be used for like downstream control tasks. So yeah, this is the thing of like, is it exactly reconstruction that is bad, or is it actually, it is reconstruction but it's in something else? In neuroscience, there's an influential theory is predictive coding, which is in a way a sort of reconstruction perhaps, and that's quite an influential sort of broad-spanning theory, and I think that's maybe one of the interesting things that could be tried in deep learning. And predictive coding is a great one where if I close my eyes and then open my eyes and can reconstruct and think about things, predictive coding is something that would, for example, be fine with that. Right? Yep.
Regarding the IWE thing you said, the importance weighted stuff, how much is it related to the fact that the encoder doesn't learn the density correctly? Because if you learn the density correctly, increasing the sample should always improve your objectives.
I can't remember the exact details of this paper. It's been a long time. Yeah.
It's more like if you're doing BAE the standard way,
Mm-hmm.
you have one sample representing the whole density, right? You have image going to density. There's only one sample represents whole of your Gaussian.
Yep.
Instead of that, now you want to represent it by more samples, so your integral would be, Monte Carlo integral would be more accurate.
Mm-hmm.
Just the objective comes from the fact that, okay, you can't cancel out the term. Obviously you could, that's how it changes, but that's the intuition that weight needs to be added. So if your variance is not calibrated, you wouldn't get the answers. The reason I say this, if you see this applied to deep GPs, exactly same thing.
Okay.
You can
Cool.
immediately see the benefits, that if you increase the sample size, you can already predict that, okay, this is the improvement, it should continuously apply. So it's not that the mode was, so from you, what you were saying that, okay, this idea was correct and it didn't work out, but I think the idea didn't work out because the interpretation was incorrect. So the idea is still...
Yes, correct. Yeah, no, I definitely agree. Like the objective makes sense mathematically, but then there is an interplay with the parametric models. Cool. So we have about 10 minutes, so quickly try and get through a bit more of this notebook. So this is the DC GAN architecture, deep convolutional GAN. Generator is just transverse convolutions in batch norm, and discriminator is just convolutions in batch norm, almost the inverse of each other. So let's go over the sort of training loop in PyTorch. So the first thing is we're going to train the discriminator to identify real data. So we're just going to feed in sample from a real data set into the discriminator, make it classify this as 1, train the network. We're going to train the discriminator to correctly classify fake data. So we're going to sample some noise from our noise distribution, push this through the generator, push this through the discriminator, and then train the discriminator such that it realizes that this is noise. And then finally what we're going to do is we're going to train the generator to fill the discriminator. So for efficiency reasons, like we take the outputs that we've already taken through the generator, push that through the discriminator. Now the objective is the other way around, like we want the discriminator to think that this is real data, optimize this objective, backpropagate the gradients through the discriminator and then the generator, and then just update the generator on this loss. So we leave the discriminator alone for this one. So that's these sort of 3 chunks here. And that's all you need to do sort of standard GAN training. All sorts of fancy things can be done now, like gradient penalties is quite common nowadays. Have spectral normalization, all sorts of fancy architectures, maybe a sort of like optimal transport loss, but this is the sort of like standard way of training these things. Any questions on this one? Nope. So again, some samples. It's also slightly crummy MNIST digits. I mean, this is a GAN that's not been trained for very long. You might notice that in comparison to the VAE ones, they're a bit rougher, but maybe somehow more realistic. And so you can see like a kind of qualitative difference in the samples based on this objective. So like this maximum likelihood objective, if you think about doing MSE on pixels to like predict images, then we'll make some very unconfident predictions about pixels and have blurry predictions. But with a GAN, like we're really operating on really a different sort of learnt metric space on this. And so you get these sorts of kind of qualitative differences in the sort of generations. Finally, autoregressive models. So it's literally, so we can think maybe about sequential models, like predicting different elements of a distribution, and it's using the simple sort of idea, which is that the probability distribution, this multivariate probability distribution, can be broken down into like this product of conditional probability distributions. So we're just predicting one element conditional on the previous one, and we just repeat this loop again and again, and we will get the kind of full distribution out of this. And so, WaveNet was mentioned in the beginning. This is code for masked convolutions of a pixel CNN. So let's just think about how this might play out in WaveNet and pixel CNN, and I'll put up this sort of samples here, just before we get into that. So you'll notice that qualitatively, these sort of samples maybe seem a lot more fluid, because what's happening here is like actually we have to sample every pixel one at a time. This is a sampling code. You can have a look at it offline. But because like the predictions are going to be conditional on what's already been generated, they tend to be a lot more kind of coherency, at least at the local level. But you may also get kind of worse global coherency because you have like these local predictions and it gets very good at that. But globally, it maybe doesn't have this ability. There's been research on like combining things like VEs with sort of like pixel CNN decoders and all sorts of hybrid models and like multi-scale models, and like these are some tactics you could use to kind of get the best of both worlds. But this is kind of what the vanilla version would do. So just to wrap up with autoregressive models. If we were to look at WaveNet, that sort of autoregressive model, we have like a waveform as input, and we want to predict this. So we're literally just going to be running convolutions over the input space, stacking convolutions. And the key thing that's going to be going on here is we take this chunk is input, and we want to be predicting this certain point. And how are we going to do that in an autoregressive fashion? Or what we're going to do is just use a mask. So this network will be seeing this sequence as input, and we'll be having to predict the next sort of point in the sequence because this thing is masked out. So it has no way to get information about this, right? So the prediction of this point, like there's no information about this directly, so it can't just predict it out. It has to use all the previous context. And so does this, increases its receptive field over the input by stacking convolutions in this case, makes a prediction, and in the case of sampling, it has to predict one point at a time. This is a weakness of autoregressive models, but it would basically like be there, and then at the next time step, we would then take our sample and then run over the input, and gradually, one by one, we'd predict it. So in the case of the pixel CNN, what is done is, again, you have a stack of convolutions. So we have some sort of image. We're going to pass this through a stack of convolutions. What we're going to do is we're actually going to mask it in a certain way to preserve the causal structure. So if you imagine this is the pixel centered, this is centered around the pixel we want to predict. We just mask out this bit so we don't have information about the pixel we want to predict, and it just takes in this context. And in the next layer, what we're going to do is we can actually take into account the pixel that we want to predict, but from the layer below. So we have the slight change in the masking. But all the context basically is extending this way when you're starting to stack the layers. So these sort of models also need to stack a lot of layers in order to get the context. So in order to predict, like, the final pixel here with this sort of structure, you'd have to stack a lot of layers, 1, 2, 3, etc., in order to get this sort of coverage. So these models tend to be deeper. And so this is the basic idea behind Pixel CNN. Did WaveNet's a sort of one-dimensional autoregressive model, and it can be trained purely on maximum likelihood, so people like it for this sort of reason. It's a sort of principal thing to be able to do, maybe. And obviously, WaveNet produces some amazing samples, so training for this objective with kind of a powerful model, lots of data, can actually work well even with max likelihood. So these are sort of some of the ways of doing deep generative models, and you can kind of combine them. You can use them as modules in other parts of your network. Maybe you want to have like a predictive model for RL. Well, you could have a VAE sort of structure, learn a latent space. Maybe you could have a pixel CNN decoder, learn a slightly better observation model. Maybe you have a GAN if for some reason like you want some really realistic predictions out for better representation learning, or maybe use it for downstream task. So you have this grand toolbox that hopefully you can take bits here and there, stick them in different places, and use them for all sorts of different purposes. And I think we're done. So thank you, everyone. I don't want to keep you from coffee, so you can come talk to me if you have any questions.